Welcome. My name is Eric Müller, and I will be presenting today the work on generating a machine-learned equation of state for fluid properties. Please note that this is a slightly different title than that which is in the program. Basically, equations of state for fluids have been a staple of engineering design and practice for a very, very long time. Equations of state are usually based on fitting a closed-form analytical mathematical expression to available experimental data. And it is just this mathematical structure and the underlying physical model that significantly restrain the applicability and accuracy of the resulting equation of state. And this has been an art that has been carried on for over a century now. Machine learning, on the other hand, is a high level, or can be understood as a high level correlation tool, and has the potential to revolutionize the way these equations of states are developed. Some examples are starting to appear in the literature. There's the work by AIChE and al. On the fitting of properties of biodiesel, and the work of Craven and al. For the Leonard-Jones equation of state. This contribution explores some of the issues surrounding that substitution of machine learning models for analytical equation of state. In general, or in particular, we describe a proof of concept, the effectiveness of machine learning's models to replicate the SAFT, or statistical associating fluid theory equation of state. To quantify the effectiveness of these machine learning techniques, we've generated a very large set of pseudodata, which is obtained from the equation of state, and used this data to train the machine learning models. This gives us an interesting handle because it avoids us the uncertainty and scatter which is inherent in experimental data. So we have a complete control of our input data, and also allows us to generate as much data as we need across the entire phase space. And most importantly, it allows us to compare and to gauge the quality of our machine learning models. We're going to compare the performance of both artificial neural networks and Gaussian process regression, both in terms of the overall accuracy, their capability to process PVT data, and also in terms of resources required in terms of the training sets. The basis of our model is going to be the SAFT equation of state. I mean the basis, I mean this is the engine that's going to produce the data. So we're not going to be using the equation of state in any form or shape to guide our machine learning results. The statistical associating fluid theory is a perturbation approach, which has recently been used to spawn a large number of analytical equations of state. And the different versions that lie around and vary with respect to the underlying molecular model, the underlying potential that's used, the accuracy of the analytical approximations employed, and the parametrizations. Of all of these models, we employ the SAFT VR-ME model. This is a third generation SAFT model, which describes a molecule as a collection of tangent beads. Each one of these beads follows the Me potential, which is an extended Leonard-Jonesian potential, where the exponent of the Leonard-Jones, instead of being 12.6, is now a lambda 6. So there's a variable in terms of the exponent. The molecules can form chains, which are quantified by the value of M, which is a number of chains, that number of beads in the chain, and the usual values of epsilon and sigma, corresponding to the depth of the potential well and the overall approximate size of the molecule. So in principle, there's 4 degrees of freedom to define a fluid. If we invoke a conformal behavior, which has been proven to be correct, we can reduce everything with respect to epsilon and sigma. And we're left with 2 degrees of freedom, lambda, which I remind you is the repulsive exponent, and M, the number of beads, and that defines a molecule. We're looking at thermophysical properties of fluids, so there's maybe 3 points which are interesting to look at with different degrees of freedom. You have the critical point, which is defined with no degrees of freedom for each type of molecule. We have vapor-liquid equilibrium, basically the density, coexisting densities, and the vapor pressure, which is then has only 1 degree of freedom, is specified once we specify the temperature. And finally, one-phase densities, or general one-phase property, which depend on the specification of 2 external properties. And in terms of machine learning strategies, we will look at artificial neural networks, basically feed-forward neural networks with stochastic gradient descent optimizers. And we'll look at Gaussian process regression as an alternative, employing radial basis functions along with matern kernels. So off to the results. The critical point is probably the easiest of these properties to fix. It's just 1 point, me fluid. So we need a large training set for this. We've noticed that with three layers in an artificial neural network, we get quite a good performance, an R-square, which is essentially 1, and a very nice distribution of the errors. When we look at Gaussian process regression, we see a similar performance. And we do get a little bit more of information because Gaussian process regression gives us as a benefit an estimate of the variance and of the error. So on the lower right-hand side of the slide, you see a distribution of that variance. The green meaning there is a very good fit. And you can see that the yellows near the corners and near the edges suggest that it is at these regions where we have the largest errors. And this is important, but it's not surprising. Remember that all of these machine learning models are basically interpolations. So it is obvious that in the corners and in the borders, there is less to interpolate to. On the other side of the box, there is nothing if you see it that way. So that also tells us a little bit about some of the strategies that we should employ in terms of fitting properties. When we looked at vapor pressures, again, we obtained with rather simple procedures some extremely good fittings. The plot on the left shows the quality of the fit that we obtain by doing a simple regression. Now, one thing that turns out to be that we can highlight is the fact that if we zoom in on the very low pressures and very low temperatures, we see that there is a large dispersion. And this is not surprising. This is just a feature of the variables that we have. And these are very small pressures, and very tiny deviations amount to a large absolute errors. So think about a pressure that's 0.001 bar plus minus 0. Which is negligible error, is actually 100% error. So in these types of situations, we employed what we know about thermodynamics, and there's no harm and no trick to this. And so if we look at the Clausius-Clapeyron equation, that the pressures should be expressed in terms of logarithm of pressures, and temperatures should be expressed instead of temperatures in inverse of temperatures. So when we make these transformations, we see that although the R-square of the fit seems more or less similar, we can see that the absolute average deviations are much less, and the fit is of a much higher quality. When we look at the results and compare the results between the predictions of the artificial neural network and the data available, we see that there is a good fit all across the board. In the left-hand side, we have the results for molecules which are made of m equals 1 spheres, going from very soft potentials, gamma equals 8, to very hard potentials of lambda equals 8, to very hard potentials of lambda equals 32. I remind you that the Leonard-Jonesium is the lambda equals 12. On the right-hand side, you have the results for m equals 10. Again, the solid lines are the artificial neural networks, and the crosses are the data, the pseudo data points that we use. And you see for this very long molecule, which typically corresponds to, for example, a C30 alkane, or equivalent to that oligomer, we have again for even very soft but and very hard potentials a very good fit. If we look at the corresponding saturated densities, this plot shows a few examples for different values of M and different values of lambda. And in general, you can see that the fit is reasonably good, although later on we'll discuss a little bit about some nuances on this graph. Although a sharp eye can probably pick up that there are some places where we don't really get a perfect fit. And not surprisingly, these corresponds to, again, to the corner states of our phase space. And so again, the model is trying to interpolate, and in these corner conditions, in terms of the M's and the lambdas, there is nothing behind them. There is nothing to interpolate with. So it has a harder time to produce that fit. Some of the things we did learn, and it's nice to point out, is the fact that we were able to do this with a relatively small number of data points, and the fitting was rather good. Our first pass at this gave us a very good model performance as described by the common statistical indicators. But when we looked at the graphs and we plotted them, they were really very, very poor. So we had to add the critical temperature and the critical density, which were fitted beforehand, to get acceptable results. And even then, when we looked at the Gaussian process regression, it converts very nicely. It produced acceptable statistical indicators. But when we plotted things and we actually looked at what we were seeing, we saw that it failed to capture the envelope of the VLE. And even when we included critical points, and even when we tried to overfit the model with over 2,000 data points, we were still unable to get a good fit. Lastly, in terms of the supercritical densities, this is a problem in which we specify temperature and pressure, so where there's a very large phase space to cover. Again, even though the training, we added a lot of data points to our training, the performance of the model was exceptional. And on the right-hand side of the slide, you see some results for the unseen data. Again, the solid line is the artificial neural network, and the crosses are the pseudo data. And this is a particularly challenging point. This is a reasonably long molecule and a reasonably non-trivial repulsive exponent. And again, the fit is as good as you would expect it to be even for an analytical equation. So in conclusion, we wanted to point out some of these conclusions. We employed both artificial neural networks and Gaussian process regression to correlate and predict the thermodynamic properties, and based simply on molecular descriptors. And I just wanted to again point out the fact that we're not here comparing to experimental data. We used the equation of state as a means to generate a set of consistent data that we could test against. So the comparison between these machine data and the surrogate data suggests that A and N from these two is probably the one that shows the most promise as being a viable technique for the correlation of properties. And the interesting thing is that the results are quite accurate. They're almost as accurate as the original equation of state. But it is important to point out that we did this without any recourse to any theoretical constructions and without any approximations. And in fact, the speed of doing this is amazing. We were able to build these in days or weeks rather than the months and years that it takes for an analytical equation of state. But one thing that's extremely and crucially important is the quality of the data, and the spread of it. If we want to extrapolate this to experimental data, you have to be extremely careful in terms of where the data is, what the bias of the data is, and what the quality of it. Because essentially machine learning interpolates this behavior, so one needs a significant amount of data which are of high quality. I finished my presentation, please direct the questions to us or contact us if you have any other questions. Thank you for listening.